The moon and other airless bodies in space are constantly being worn away. Space weathering is a process that involves, among other things, the solar wind that results in changes to the structure of exposed surfaces. Understanding this phenomenon will lead to greater knowledge of the formation and lives of objects like the moon and asteroids in our solar system. U.S. researchers recently published an article describing the latest in space weathering simulation and experimentation, a document that serves as the basis for this video. We'll cover what space weathering is, as well as the results and the new experimental methodology that led to these findings. An object in space is subject to solar wind, radiation, and collisions from other objects. We'll look at the effects of the solar wind. Solar wind is a plasma composed of hydrogen and helium that spews out of the upper layers of the sun, also known as the corona. Lunar regolith is a dusty layer of rock covering the moon. Over time, the effects of solar wind and the associated hydrogen-helium bombardment results in the formation of a material known as nanophase iron. When you look at something very closely, the individual grains within the material become apparent. A nanophase material is when the size of these grains is less than 100 nanometers. It turns out that a nanophase material is far more brittle and hard than normal materials. Iron oxide, or rust, is abundant on the moon. For nanophase iron to form, this rust must lose its oxygen atom. How this happens is not fully understood. The possible reason suggested in this study is that the solar wind reacts with the oxygen in the iron oxide within the regolith to form hydroxide and water molecules. These molecules diffuse through the regolith until they reach the coldest part of the moon, the lunar poles, leaving behind only pure iron. To simulate the process of space weathering, polished units of a mineral known as enstatite were placed onto a wafer of silicon and then subjected to plasma source ion implantation using hydrogen and helium. The samples were then inspected using an electron microscope. Enstatite is an orthopyroxene, a mineral with a special type of internal structure that is commonly found in lava, meteorites, and the surfaces of planets. The polished enstatite samples were placed onto a silicon wafer to act as impurities in order to approximate the surfaces of the moon that have the capability to form nanophase iron. Plasma source ion implantation uses high voltage filaments to ionize a gas in order to bombard and implant ions of the gas onto a material. Tungsten filaments were specifically chosen for this experiment because they approximate real solar wind by providing a lower energy bombardment. When an ion hits a material, there are several possibilities as to what will happen next. The ion can be reflected, it can knock off electrons, it can be implanted within the material, or it can cause sputtering. Sputtering happens when an ion makes a collision and then knocks off atoms from the material. The samples of the orthopyroxene and enstatite were analyzed using an electron microscope. To protect the samples from the electron beam of the microscope, they are coated in a minute layer of gold using a technique called sputter coating. Sputter coating bombards gold with energetic particles to knock off gold atoms. These atoms will then attach themselves to the enstatite sample. The samples were then coated in an even thinner layer of carbon using an ion beam assisted deposition, which is a process similar to sputter coating. Then, the lift-out sample preparation technique was used, where an energetic beam systematically cuts away at the sample to make the surface transparent to electrons. The results of this experiment are summarized in graphics made using electron energy loss spectroscopy. Electron energy loss spectroscopy reveals the number of any particular type of atom by using a beam of electrons fired with a precise amount of energy. Some of these electrons lose energy after colliding with the sample material, a value that can be measured. By measuring and plotting this energy loss, the atomic composition of the sample material can be inferred. It was chosen for this experiment because of its relatively weak electron beam requirement, limiting the potential for sample damage. Consider this map of the distribution of the most important elements within a section of the orthopyroxene sample when exposed to helium. From left to right, concentrations of iron, oxygen, and magnesium are given. Nanophase iron is indicated by spots of higher relative concentrations of iron and lower relative concentrations of oxygen. Directly below the protective gold layer, we see that iron and magnesium have a band of low concentration while oxygen has a relatively higher concentration. This is due to the fact that sputtering is more likely for certain materials due to energy transfer efficiency. This is called preferential sputtering. Also note that on the right side of each picture, a line of low concentration is visible. This is damage from the electron beam. The orthopyroxene exposed to hydrogen looks similar to the sample exposed to helium. However, the iron appears to have clumps of nanophase iron instead of a more or less clear band. Known as Oswald ripening, these clumps grow due to thermodynamic processes that favor larger nanophase particles. Space weathering is constantly happening to exposed bodies in the solar system. To learn more, scientists are developing sophisticated techniques to accurately simulate the actual phenomenon here on Earth so they can scrutinize the process. The blast of the solar wind has the power to change the soil composition of even enormous bodies like the Moon. So much so that the elemental spectra of the satellite, when viewed through a spectrometer, has been changed to reflect the amorphous balance between iron oxide and nanophase iron. Will the Moon eventually be covered in vast sheets of pure iron? Maybe this process is only transient and shows humans a tiny piece of the enormous whole. The experiments we perform on Earth are rapidly becoming more complicated and more enlightening.